So a little bit on properties of ethers. The bond angle is about 109. Dimethyl ether is 112. Methanol is 109. The only difference is the size of the groups that are on the oxygen, bonded to the oxygen. The bigger those groups are, the bigger the angle gets. Okay. A lot of people, for second period elements, so lithium all the way through neon, they have to obey the octet rule because they don't have d orbitals. So hybridization like rules there, and you end up getting nice tetrahedral shapes. You get nice trigonal planar shapes. You get nice, things that you would expect. It turns out as you go further down the periodic table, the atoms of the central atoms are so big that they don't always occupy those angles that you would expect for 4 groups or 3 groups. So like NH3 ammonia, right? Just little, again, side notes. If I did NH3, like, wait a minute. There we go. I'll go back to a different colored pen. If I do NH3, what's the bond angle between the hydrogens? You guys remember? Like 100 and, it's not 109, it's like 107, right? But it's pretty close to 109.5. Kind of makes sense because in water it's 105, but you have another hydrogen and the group takes up space and it spreads out. It kind of makes sense. Right? So if we go one row down the periodic table, really crazy, and I do this, what do you think the bond angle is? Well, the top one's 107 in periodic properties. That should be like, 109, 107, right? It's 90. Why? Central atom's so big, the little hydrogens that are sticking on it, they don't repel each other. So they stay in unhybridized orbitals. They're just in the p orbitals. Now, if you put methyl groups there, then they spread out, and they're closer to the 109 that you expect. But yeah, most of the shapes of molecules below the second period, like you just have to do it experimentally. You have to look at what bond angles are. Okay, anyways, that was a little side note. So this nitrogen, and these oxygens, hybridization is sp what? 3, right? 4 groups, sp3. What's this one? No, unhybridized. The bond angle is 90. The 90 is telling us more about the hybridization than the actual structure is. Okay, but for ammonia, it's 107, so it's sp3. Right? Sorry. I like doing that to people, but it's very painful sometimes. All right, some of the properties of ethers are governed by the fact that in ethers, I have 2 R groups. Oops. Actually, is that on the next slide? Yeah. So in alcohols, going the wrong way. In alcohols, I have hydrogen bonding that takes place. In water, I have hydrogen bonding that takes place. Viscosity, intermolecular forces, right? Viscosity, boiling point. All those things are higher because of hydrogen bonding. That is for their molecular weight. Water can make hydrogen bonds with 2 other water molecules. Alcohols can make hydrogen bonds with 1 other molecule, right? But ethers can only be hydrogen bonded to and can't actually hydrogen bond themselves to something else because they have the 2 R groups instead of the hydrogen. So in principle, then, what that means is if you're looking at boiling point trends or melting point trends, right? Ethers will be somewhere in between alkanes, which have no intermolecular force other than dispersion forces, and alcohols, which have hydrogen bonding. Okay. So that's what this is. Here's ethanol, diethyl ether, and propane. Right? Propane is alkane. Intermolecular force is dispersion forces. What's the other name for dispersion forces? London. $200 each way this summer. Wow Airlines. Wow. Iceland's biggest international, whatever that means. It is. It's like the #1 airline for people in Iceland to go to Europe. It's like $200 from there, but they're having a deal this summer they're opening up access to San Francisco. So you go to Iceland for $99 from San Francisco. Sorry. It's been on my mind lately. I tell people, if you're on the first flight, that's great. It's the last flight you have to worry about, because they skip all the maintenance and stuff. They're probably clean when they start. Dimethyl ether, right? Has dipole-dipole. And ethanol has hydrogen bonding. Oy, oy, oy. Internet's slow. And dispersion, dipole-dipole. All of them have dispersion forces, but the principal force for ethanol is hydrogen bonding. Dimethyl ether or diethyl ether is dipole-dipole, and then dispersion forces for propane. So if you look at the boiling point trends, it makes pretty good sense. -42 for propane, 78 for ethanol with dimethyl ether in the middle. If you look at a series of ethers, okay, you have dimethyl ether at -25, but diethyl ether, that's the one that we use in lab. That's 35 degrees Celsius, right? And then dipropyl ether is 91 degrees Celsius. So these are all three are governed really by dipole-dipole interactions and then increasing dispersion force. Because remember, dispersion force, the longer the molecule gets, the more the forces add up between different parts of the molecule. So if you put another ether on top, then what happens is you have dipole-dipole going this way, but then you also have these dispersion forces between every part of the molecule. And those little like hooks, right, for force add up. It's kind of like Velcro. It's the analogy I use in my 1A class, like Velcro. Little hook in Velcro has very little force, but if you put a whole bunch of Velcro side by side, that's like a long molecule. It's really hard to pull the two apart. And so that's what these longer ethers have. We like to use them as solvents because, one, they have low boiling points, so we can evaporate them very cleanly after you make something. If you guys made your product on Thursday of last week, there's a chance to get it up the drying agent. You'll have to actually add some ether because it probably evaporated out. Even though it's sealed, because its boiling point's only 35, diethyl ether is only 35 degrees Celsius, it's constantly forcing its way out of the container. It's been cool in here, though. Like the other day, somebody had methylene chloride in their drawer, and they took the flask and they just capped it really tight, and I think it got hot in here over the weekend, and you could tell that it had built up enough pressure up that it released, and all their product was spread like in a circle around there. It was pretty sad. Around their, like the round bottom flask, right? Ether's worse. They still had stuff in there, but I mean, it was like, we were trying to figure out, like, there's no cracks, no leaks, but there was like spray all over the place. I'm like, oh, it just probably just vented by itself, so. All right, so relatively low boiling points allow them to be evaporated. The dipole moment allows them to stabilize charge, so they're a polar aprotic solvent, right? Which is important because it stabilizes transition states and stabilizes, remember, we're doing a lot of reactions, substitution reactions, right? So the nucleophiles all have charge. So if you don't have some polarity in the solution, you can't get them to dissolve. So it helps with the solubility. Okay? Well, that's only partially true, but generally true. Okay. And they're not protic, so that's good for things like the Grignard reaction. It's good for things like the acetylide reactions, that you don't have proton sources. So they're not acidic is, I think, the simple way to put it. Only conditions in which ethers are not good is at very low pHs. And then ethers begin to decompose. Okay, we'll talk about the reactions of ethers in a little bit. Yeah, so metal atoms with full or partial positive charge can be stabilized by ether solvents. So like in the Grignard reaction, you have the magnesium with a very large positive charge connected to the carbon. The oxygen electrons and the dipoles are able to stabilize that. Okay. And I just said it's also good because it's aprotic. And this is why I was doing the simulation that failed so horrible. Actually, it worked the first time I did it. When I tried to re-simulate it, then that's when it failed horribly. This is these are known as crown ethers. There's this, for example, 12. If you count the 12, it's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's the 12 atoms. 4 means 4 oxygens, and it's usually symmetric, so you don't have to really designate much else. So this is a crown 4, this is a 15 crown 5, and this is an 18 crown 6. The reason those are cool is because they're the pocket that they make in the middle, right? If you think about what you have inside of each one of these, this pocket, that's where the negative side of all the dipoles exists, and that's where all the lone pairs are. So if you have a cation and you bring it in the presence of a crown ether, it'll get sucked into inside that pocket, especially if it fits into the pocket. So if I try to do like a potassium ion in here, well, the potassium ion in respect to the molecule is kind of like that big. The K plus ion, it actually fits right into here, into this crown 60. Okay. So part of the difficulty of getting salts or like ionic compounds or nucleophiles into solution is that they don't dissolve because the cation and the anion can't be supported by the solvent. This is what we say. It can't be solvated very well. So crown ethers give us a way, right, to pocket the positive ion. And then this part out here, this is all nonpolar. And if you modify it, you can change, to varying degrees the polarity of the outside. So what it does, it takes a positive charge, hides it. Like in those movies where they try to break into a fortress and they hide somebody in a basket, or like the Trojan horse, and they hide people in the horse. It's like the Trojan horse, right? You put the enemy on the inside and you bring them through into the solution. That's kind of the idea. Okay, so this is what they look like. This crown ether, this oxygen's going up and that one's going down. When the one that's going up, you can see all the negative charge. This is what it looks like. This is the crown 6 ether, I think. Yeah, crown 6. This is what it looks like when it has a potassium ion in it. So now you can get a potassium ion in there, and then along with the potassium, you could bring in a nucleophile. Okay. One of the reasons that let's see. So normally metal ions are not soluble in low polarity solvents, right? So crown ethers help with that solubility, and that help us increase the concentration of a nucleophile in the solution where it normally wouldn't be present. Okay. Fluoride can actually be a really good nucleophile, but there's solvent effects that we have to worry about with fluoride. Because when you put fluoride in a solvent, because of its strong negative charge and high electron density, tends to attract solvent to itself. So that really decreases its ability to be a nucleophile. So one of the things we talked about like last semester is that if you want to use something like fluoride as a nucleophile, it's best in aprotic or low polarity solvents because the solvent won't complex to it. The problem is you can't get like potassium fluoride to dissolve in low polarity solvents. It's not soluble in there. So what you can do is you can mix the crown ether with potassium fluoride, and it'll actually dissolve in benzene. So benzene is completely nonpolar, right? But now you have your nucleophile and nonpolar solvent, and then the fluorine is not complex to anything. It's a very strong nucleophile. Okay. So reactions like this, right, which you couldn't do without the crown ether, can be done because the crown ether helps to bring that fluoride nucleophile into solution. Well, it brings the potassium, and then the fluoride sort of comes along with the potassium because of the charge. Depending on what you want to dissolve, right, you can use different size crown ethers. So you can do the 18 crown 6 or the 15 crown 5 and the 12 crown 4. Those all fit the different cations in the first group of the periodic table. So lithium, sodium, and potassium. And then with those, you can bring in other nucleophiles or other reagents to get to dissolve. I think we're going to do the experiment this semester where we use ammonium ions to do a similar thing. It's called a phase transfer catalyst. So when we get to there, we'll talk about phase transfer catalyst, a little bit on crown ethers maybe too. Okay, so how do you make ethers? Well, a simple way is to, if you want to make a symmetric ether would be like dimethyl ether or diethyl ether or dipropyl or diisopropyl, where you have two of the same alkyl groups, okay? One simple way is to just reflux it in acid. So ethanol, right, boiling point 78. You reflux it with strong acid. It'll protonate, and then you get an SN2 style reaction because it's primary, right? So you can only have SN2. That'll form the protonated ether, which then the solvent picks that up, so it's a catalytic process. You'll pick up the proton back up. And you end up with diethyl ether. Diethyl ether's boiling point is 35 degrees Celsius. So as soon as it forms, it's above its boiling point and it leaves the solution. So even though it might not be like a very good reaction, equilibrium-wise, you can force it to completion simply by just collecting the distillate, okay, allowing it to distill out. How is it a dehydration? How is it a dehydration? What does dehydration mean? It lost to water, right? I'm not sure. I leave these are questions that, the book puts in there, but it's to help point to your mind some of the key things that happen in the mechanism. It's that. All right, that comes off as a water. So it's a dehydration reaction. Now, if you want to make asymmetric ethers, you could put ethanol and methanol in a pot, in a reaction vessel, add sulfuric acid to it. Reflux. What's going to happen? What do you get out of that? You get methyl ethyl ether, you get dimethyl ether, and you get diethyl ether. So you get a whole mixture of things. So if you want to make an asymmetric ether, you have to do something else, okay? The something else that people like to talk about a lot is this reaction. Make sure I'm on the right page. Yeah, it's this reaction. It's the Williamson ether synthesis. Here's an alcohol, right? And here's an alkyl halide. And the idea is to take the alcohol, produce a nucleophile out of it, and use that to attack an alkyl halide. Now, an alcohol, just note, right, can be produced a couple of different ways. That's the NaH or NaS. NaH is just sodium hydride. That's an off-the-shelf thing. Or you could use sodium to directly reduce the hydrogen off of the alcohol and then at the same time produce sodium hydride. That was a mechanism I showed before, so I'll just go over it real quick. At least this is the way I see it happening. Not drawing all the other lone pair electrons. And NaH. Now the NaH can do just like it, you see it above the slide, on the slide above it, right? Sodium hydride is what's produced down here. So we could find an alcohol molecule and convert it to the alkoxide ion. Okay. But it can also, you've created this oxygen radical, which can produce the alkoxide ion directly when it accepts another electron. And you get this. So, in essence, 2 moles of sodium produce 2 moles of alkoxide ion, 1 directly and then 1 indirectly because it makes sodium hydride. Okay. So basically, it's 2 to 2, stoichiometry is 1 to 1. And then out of this, right, this reaction here, the other thing that comes off of this reaction is hydrogen gas, so that bubbles out of the solution. And definitely, we'll do this later this semester. You'll see it in the lab. You'll see the little bubbles. I'll do it as a demo because we actually make the alkoxide ion for one of our experiments. So, nucleophilic attack, asymmetric ether. Okay. So, characteristics. They make a lot of slides on this, and I don't want to flip a bunch of slides. What are the characteristics of this? And what are the characteristics of this? Okay, well, RO minus, strong base. Alkyl halide, well, that's a methyl alkyl halide. Okay. But the alkyl halide needs to be methyl or primary. Because if you have a strong base and a secondary alkyl halide, what happens? You get an elimination, right? You get E2 elimination and you get an alkene instead. So there's some limitations to this method, right? You have to be able to make a primary alkyl halide or at least a secondary alkyl halide, but then you have to expect a lot of other byproducts, okay? Yeah, so strong base, methyl or primary alkyl halide. Let me see. That had actually some of the notes I was just saying on it, that last slide. They used the same slide and added different text to it. So I'm going to skip over. So now, take a look at this. They give you 2 different pathways. This is MTBE. You should all say boo. MTBE. That's the stuff they put in our gasoline. You remember the MTBE in your gasoline? It's to oxygenate your gasoline. Do you guys remember what they figured out about it? It was leaking out from the gas tanks and going into our drinking water. It's really soluble, it turns out. So, yeah. I'm just expecting a whole bunch of other stuff to come from that. But anyways, yeah, they stopped putting it in gasoline. Now they just put ethanol, I think. But that has other issues. So they have 2 ways to produce MTBE. One is to produce the alkoxide radical that looks like this. Oops. Go back up. One is, right, using NaH. That's step 1. You're going to produce this. The other is to use NaH and produce this. So one of those works and one of them doesn't, and unfortunately in the image they show you which one doesn't work. They show you the one at the bottom doesn't work. Why doesn't the one at the bottom work? Too sterically hindered. Can't do SN2. It's tertiary alkyl halide. Get elimination. Right? So, I mean, those things go together, but yeah. So too sterically hindered for an SN2. So you end up getting, actually from this reaction, you end up getting, oh, that looks horrible. You get this isobutene out of that. On the top one, that'll work because that's a methyl. This is methyl. Remember, methyl or primary alkyl halides are what you do this with. So they'll give you a good yield of MTBE. Oh, so, yeah. So what's the goal here? Synthesis of an asymmetric ether. And this is by the Williamson ether synthesis, all right? Use the least hindered alkyl halide. So you're saying, well, what if it's just always primary, right? Primary versus primary, but you could have a situation like this. Those are both primary, right? Because that's a primary alcohol and that's a primary alcohol. But this large group over here makes it more sterically hindered. Even though it's away from the nucleophilic site, it's huge, right? So you would prefer to have the one on the right be your alkyl halide and then the alcohol be your sterically hindered one. Okay. All right. So if you're going to use William ether synthesis to produce this molecule, all right, what are the reagents you use to do it? So again, you look at the molecule, right? Which side's going to be the alkyl halide? Yeah, the left side, because I didn't say yes the first time, right? Yeah. Yeah, the left side, because that's the least sterically hindered side. So you're going to use this. Oh, you're going to use this as your alkyl halide. And then that means your other side's the alcohol. Now, this is kind of one of those trick questions of organic chemistry. So this will be your alcohol. The reason it's a trick question because it's an SN2 reaction, right? But the inversion takes place over here. So this stereochemistry is unaffected. This is the same. Right? Because what people will think, right, oh, it's SN2, so I guess stereocenter, I'll invert it. But only the alkyl halide gets inverted, and the rest of it stays the same. And that NaH, and this is 2 right here. That's what you'll add. Okay. So the other way to produce ethers, and this is how you would produce, for example, ethers that look like, I don't know. Let's say you wanted to produce that ether, all right? Well, to produce that ether, right, they're both secondary. You can't use a Williamson ether synthesis because since the alkyl halide will be secondary and you're generating a strong base, you'll get an elimination. So the reaction is the one I mentioned actually last semester. They're talking about it now, right? That's here. It's the, well, you guys know the oxymercuration-demercuration reaction where you form the cyclic mercuric ion intermediate and then you attack with water and that produces the alcohol. The alkoxymercuration-demercuration is in substance the same reaction. Okay, same mechanism. The only difference is instead of water as your solvent, you have an alcohol as your solvent. Water is the nucleophile up here. The alcohol is the nucleophile up here. And when you attack with this as a nucleophile, you're going to have RO and another carbon, so that's your ether functional group. Okay, so I'll go over the mechanism for it in a second. But I wanted you to see that these two are essentially the same. In your reaction notebook, Hopefully you're getting to that now, that little bit of guilt that I'm giving you because it's due next week at the exam for 10% of the grade. Sorry. You can write this as 1 and just say RO or H2O, or ROH, where R could be H or alkyl. Right? So here's the mechanism. The way I do this is slightly different than what's in the book. I'm going to draw it all out. Oops. So, the mercury, the way I do it is I leave the OACs on. The way the book does it is they have one of the OACs leave and then leaves the positively charged mercury. But it goes like this. D electrons from the mercury, and then this leaves. Oops. Then from here on out, what I do and what the book does is exactly the same. Or do's, if you say it that way. And this is one of those cyclic intermediates. It is essentially Markovnikov addition. So when the nucleophile comes in, and that's the alcohol in this case, it could choose 2 paths. It could go like this and attack the carbon on the left, or it could go like this and go to the carbon on the right. That's not the one that happens. And the reason is at this carbon here, because you have more alkyl substituents on this carbon, the transition state, oh, I left something off. The transition state has a positive charge. Because the transition state has a positive charge, the breaking of the bond on the left side over here, right, puts the positive charge in the transition state in the most substituted position. It's the same argument that you make for carbocations. Carbocations form in the most substituted position. Transition states for carbocations prefer to go through transition states will give you most positive charge through the carbon. Okay? Then a miracle occurs. Remember, that's this reaction. It's not all a miracle. Oh, I'm going to say minus H plus. Oh, wait, I just got rid of my H plus by doing that. Never mind. There we go. It was like that, okay? And then you hit it with sodium borohydride. So the sodium borohydride, I'm pretty sure this is the first step. It's just a hydride transfer. But then after that, you get like mercury metal, and you get a bunch of other stuff that comes out of the solution. So really, that's when a miracle occurs. You don't have to do the hydride transfer. Just let's assume that potentially is part of it. It makes some sense that that's the way it is. But it's not clear that that's what it is, I don't think. Or I shouldn't say that's not clear that's what it is. It's clear that's not the only thing that's going on, apparently. Now, the reaction is Markovnikov in nature. And because the leaving group, the cyclic ring, is attacked from the bottom, and the alcohol appears on the opposite side of the mercury, it is essentially an anti-style addition reaction because it comes from the opposite side. Okay, so let's talk about reactions of ethers. So that's how you make ethers. There's other ways you make ethers too, but we'll go into all of them. The reactions of ethers are that they're unstable under acidic conditions. So a couple of things can happen. If I protonate an ether, then all of a sudden the oxygen becomes a good leaving group because it can leave from one side or the other and produce an alcohol, which is a stable molecule. So now it's possible for a nucleophile to attack this. And if you were to do a nucleophile, the nucleophile would principally attack this one first, all right, and then displace this as the alcohol. The reason it would attack this side first is because this is a less sterically hindered side, so a nucleophilic attack prefers to attack here rather than over here on the ring side. So here's a mechanism. If you use like HCl or HBr or HI or even HF, a lot less so with HF, but this is the mechanism how the ether will get cleaved. Okay, is that first it picks up the proton from, oh, I lost my connection. Let's see if this works. Yes. Seem to disconnect it from my computer, so I will point with a pointer. Yeah, so the oxygen gets protonated by hydrogen. The halogen that's left from the protonation step acts as a nucleophile. This is a symmetric ether, so it's going to attack either side. But the typical thing is that it attacks the least sterically hindered side first. So it'll attack a methyl group. This produces the alcohol and an alkyl halide. But then what happens is in the reaction, because you have an alcohol and a strong, what's called mineral acid, like HCl or HBr, the alcohol gets converted to alkyl halide too. Okay? So in essence, what happens is you have an ether, and at the end, the first one gets converted to an alkyl halide, and then eventually the second one's converted to an alkyl halide. This is that same mechanism that we saw in like chapter 9, right? Protonation and then substitution. If it's tertiary, it goes by SN1 mechanism. That kind of stuff. Make sense? All along here. Let's see if I can. Hey, it worked. Okay, so in this mechanism, okay, this is kind of the exception to the rule. The products are so here's the question. Why is that the exception to the rule? Okay. Just for note, right? That's the one that formed first. There isn't something funny that happened, right? It protonated. Nucleophile is a halogen. That's how the first product gets formed. After that, the product that you have is actually this. And in the earlier example that I pointed to, this got protonated by the excess. To form this. Okay. which is probably still happening. But then what would the next step be if this followed the same mechanism as up here, right? The halogen would have to do an SN2 style reaction and kick this off. And this is the part that doesn't happen. So the question is, why doesn't it happen? And the simple answer is the benzene ring is flat. In order to backside attack, it would have to come from inside the ring. And it can't get in there. Okay? If you think about a benzene ring being this shape, the nucleophile would have to come in here to displace that. And it can't get inside the ring, in part because, well, there's not enough space. And the other part is those carbons are all sp2 hybridized. So there's this cloud of electrons that is on top and on bottom that act as a barrier for the nucleophile to actually get in there. Okay, so one, it has to get, the nucleophile has to get to that inside space. And the other is this pi cloud doesn't allow the nucleophiles to do that. Now, it turns out, what we'll cover in later chapters, a couple of chapters from now, there are certain situations where you can get that to happen or appear to happen. And one is sometimes that's not how it's happening. There's another mechanism. Okay. And the other one is you have to use really strong, what they call electron withdrawing agents, to pull the electron density out of the cloud so the nucleophile can get in there. Okay. So it doesn't happen in general. It has to be set up to happen. Okay, so promoting cleavage, that always sounds weird to me. Most effective, HI, least effective, HF. Why? What's the, right? You could tell all your friends, my professor was promoting cleavage in class. I just hate it when I have to say things like that. I'll have to tell that one to my wife. She'll just probably hit me, but that's okay. It's better she hear that I said something stupid than she hears somebody else tell her that I said something stupid. So HI, stronger acid. All right. HF, very weak acid. Now HI, HBr, HCl are all strong, but HF is weak, so there's very little protonation going on there. Right. But then beyond that, iodine is just the best nucleophile. Right. In protic solvents, but remember we're talking about ethers and alcohols that are produced. Iodine is just a better nucleophile because it's so large. They do mention that this is an acid-promoted reaction than acid-catalyzed, simply because the acid gets used up in the reaction. It does make it faster. So like, remember we talked about acid-catalyzed reaction. Catalyzed reaction, the catalyst gets regenerated during the reaction and makes the reaction faster. In this case, this is acid-promoted because it makes the reaction faster, but then the halogen gets used in making the alkyl halide, so none of it gets regenerated again. Okay. Oh yeah, let's do this. Predict the products for the reaction below and draw the complete mechanism. Okay, let's predict the products first. What are the products? You can do it by name. Just put bromines, right, where the oxygen is on each. So on a BR here. And on this other one, in principle, it is this. Wait, it's not that. It's this. Bromide is a strong nucleophile, weak base, so it'll do a substitution reaction on elimination. And it'll be SN2 then. then what happens? It's the mechanism. Oh yeah, the mechanism. So the mechanism. First thing, I can't write very fast on my iPad today for some reason. Protonate. And then the bromide will attack. So the first product is this, plus cyclopentyl alcohol. And then this will protonate. I'm going to say plus H plus because I'm running out of space. Get that, and then the Br2 comes in as a nucleophile, or the Br comes in as a nucleophile. Backside attack. Oh, that was horrible. And that gives me that. If you could follow that. The good news is I'm still recording. You guys follow it? Yeah. They say, recall from section 11.9, ethers can undergo autooxidation. I didn't cover it, so now we're going to cover it. Okay. Ethers, in the presence of oxygen, undergo autooxidation. And one of the dangerous things about diethyl ether, which we used in lab, is that if you let it sit long enough and the oxygen gets in there, it makes these what they call hydroperoxides, which if you have like a glass cap and you have the peroxide in it and you twist it and the peroxide's formed in the interface between the glass joint, right, and the glass cap, it forms there because that's where the ether vapors come out and that's where they meet the oxygen. When you twist it, it blows up. Yeah. So we use plastic caps and we buy enough ether and use it every year so that we don't have a lot of excess. Now, I'd like to say that's true. That's what we try to do. But then the last lab tech didn't get rid of the old ether from like 10 years ago. So there's this old rusty bottle, metal can in the refrigerator. And then he bought, like for some reason, bought so many liters of ether and we can't go through it all. So now we've had it for like 4 years. And we have to test it. There's actually peroxide test strips that we use. Okay, so the reaction goes like this. You get an initiator, right? It can come from light. It can just naturally form. The initiator forms this radical here. And the thing about this radical is it's actually stabilized by resonance from the oxygen electrons, right? So you get this radical that forms here. This combines with another oxygen atom. They showed the oxygen like this with the electrons on either side, but it combines with an oxygen and then forms this peroxy radical. And then this attacks another, right, ether, and then produces the ether radical, which is what you have up here. So this is actually all the propagation steps right here. Okay, and this is the very explosive ether, peroxy ether.
Do you even know that mechanism?
You should be able to do it, yeah. If I showed you the product, say it's a radical reaction, yeah, you should be able to do it. The termination steps are coupling steps like these, so you end up with these like this, but overall reaction looks like this. Right, ether plus oxygen produces a peroxide. And now we're going to name epoxides, but I think I'll stop because I don't want to start this right now.